Okay, now as we have seen, there are multiple levels of infinity. Now it becomes more difficult to navigate in cardinality, let's say, and especially when you need to prove that two sets are in cardinality equal. Our definition might be difficult to fulfill. Our definition, if you remember, was if there is a bijection from, let's say, set A to set B, then they are equal in cardinality. But in all cases, it might not be easy to come up with bijections from a set to another one. It may not be obvious at first sight. So Schröder-Bernstein theorem is very important in this regard, and let's see what it says. If there exists an injective function from set A to set B, remember what injective function is. It's one-to-one. Injective is one-to-one, surjective is onto, and bijective is both of them, essentially. That's it. If there exists an injective function from A to B, and there exists an injective function from B to A, then there exists a bijection from A to B. Okay, I'm not going to give the proof. It's not very straightforward due to the axioms you need to use. What is assumed and what is an axiom. It's a little bit involved, so we are not going to go there. The mechanism is a little bit more uh, understandable. Let's say if you can look it up, it's not that difficult, the mechanism, but the rigorous proof itself is a little bit involved, so we are not going to go into that. But you see, this theorem, it looks, well, it looks a little bit trivial because when you look at it, yeah, it should be like this. You say that, but the proof is involved. Now, let's really understand what it's saying. If you can find a one-to-one function from A to B and vice versa, then their cardinalities are equal. Now, the crucial thing here is it doesn't have to be a bijection, it's one-to-one, so it may not be invertible. Therefore, do not confuse this, okay? The functions you come up with, okay, the one-to-one function from A to B and the one-to-one function from B to A doesn't have to be inverses, okay? They may be unrelated functions. Essentially, you are trying to find two functions from A to B and B to A. Both of them should be one-to-one. And remember, if you can find a one-to-one function from A to B, essentially what you have is cardinality of A less than or equal to cardinality of B. And if you can find a one-to-one function from B to A, then the cardinality of B should be less than or equal to A, cardinality of A. And if this is the case, then they are equal in cardinality. Not because this implies this. Because, well, if numbers here, let's say m less than or equal to n less than or equal to m, if you have these two simultaneously, you can safely say that n equals m as long as n and m are finite numbers. Here we are talking about infinite cardinalities, so it's a little bit complicated than that, okay? We cannot say that when this is satisfied and this is satisfied, directly this should be the case. It's not as trivial as that, okay? I'm going to tell you that much, but we are not going to go into the proof. Essentially, when you want to prove the cardinalities of A and B are equal, but it is difficult to come up with a bijection between the two, what you can do is find not a bijection, but a one-to-one function from A to B, and then another function which is one-to-one from B to A, and that's it. Okay, so here's an example. We are going to prove that the cardinality of the sets, well, the open interval 0, 1, and the half open interval 0, 1, where 1 is included. You see 1 is included in one and not in the other one. The only element that differs from one set to the other is just 1. So it's not really straightforward to come up with a bijection between these two sets, because, well, you have a continuum and you add just one element to it, you obtain another continuum because it's an interval rather than a list of elements. And how do you come up with a bijection between the two? It's not very straightforward. Okay, so instead of doing that, find two injective functions from each other. Now, from the open interval 0, 1 to the half open interval, because this one is the subset of the other, identity function works as a one-to-one function, because any element here is an element here, so itself is going to be in the codomain. So that is simple. What about the other way around? From 0, 1 half open interval where 1 is included to 0, 1 open interval. Now, to include this one, for instance, x over 2 works, because with the function x over 2, well, 0 is excluded anyway, but all the other numbers up to 1, their halves are in this set, and 1 is included in this set, and its half, 1 over 2, is in this interval. So this function is a one-to-one function. You see, both of them are not bijections. They are not onto functions. Both of them are not onto, but both of them are one-to-one, and that is sufficient. By Schröder-Bernstein Theorem, their cardinalities are equal. So that is the beauty of this theorem. Okay, another one here, we can also prove the cardinality of this open interval is in fact equal to the cardinality of all real numbers. The entire real line in cardinality is equal to this just open interval. Okay, so how am I going to do that? Again, finding a bijection is not really straightforward. So I'm going to define a one-to-one function from this open interval to the set of reals. Again, since this is a subset of this one, identity function works here. What about the other way around? From set of reals into 0, 1, the open interval, I need to find a one-to-one function, and this one works. 1 over 1 plus e to the power x. Well, if you just check out the limits, as x goes to negative infinity, e to the power x goes to 0. So at the limit, this goes to 1. But, well, since negative infinity is not in the set of reals, this function is not going to take the value of 1. So it doesn't harm that this is an open interval here. What about the other way? If you take x to positive infinity at the limit, e to the power x goes to infinity, so 1 over 1 plus e to the power x goes to 0. Again, it just goes to 0. It doesn't take the value of 0. So this is a function which is one-to-one from set of reals to this open interval. Along with this one, so this one side and this one the other side, using Schröder-Bernstein theorem, we have shown that the half open interval from 0 to 1 has the same cardinality with real numbers. Okay, so the real continuum, the entire real line, has the same cardinality of, well, using this logic, any open interval of real numbers. As small as it is, a half open interval on the real line has as many elements as the entire real line. It's a confusing result, but it's the truth. Finally, as an example, we can also prove the Cartesian product of natural numbers with itself is countable, right? Now here, I'm not going to give you a bijection. Well, we already have Cantor's pairing function, but we'll do this in a different way. We are going to define one-to-one functions from the Cartesian product to naturals and vice versa. From set of naturals to the Cartesian product, this is easy because you just have one natural number. Use it as one of the components of the ordered pairs, like this one. And this function is one-to-one from naturals to the Cartesian product. What about the other way around? Here you have as your input, you have an ordered pair. And for every ordered pair, you need to find a function that produces a unique value in set of natural numbers. And this one, 2 to the power x times 3 to the power y, is such a function because you give me any ordered pair, 2 to the power x times 3 to the power y is going to produce a different value if you change the ordered pair xy, even if you swap them yx, or if you increment one of them x plus y, x plus 1 and y, or if you modify either of the components, the result is going to be different. And since the factorization of integers is unique, this function actually, if you can give me a number that satisfies this, where x and y are integers, I can uniquely find what that x is and what that y value is. Okay, so it's a one-to-one function from set of ordered pairs, the Cartesian product of natural numbers with itself, to set of natural numbers. So you see, I can also use Schröder-Bernstein theorem to prove that, in fact, in the general sense, n to the power k, where k is an integer, a positive integer, is a countably infinite set.